Assignment number 4, dealing with continuity. Number 1, we're given the graph of g, and for starters we have to state the values of x of which g is discontinuous and explain why. So the easy way to identify where we have discontinuities would be if we were to trace our pen across the graph and figure out when we'd have to pick our pen up off the paper in order to continue to draw the graph. And we can see that it happens in 3 different occasions. At -3, at x equals -1, and x equals 1. Now, more importantly, explain why. Now we know that discontinuities are occurring because one of the 3 conditions is failing. In the situation of x equals -3, the limit does not exist. That condition fails. All right, so the limit as x approaches -3 of g of x does not exist. That's why we have the gap there, the jump. In the situation with x equals -1, well, now the limit exists because we can see that the 2 pens are going to be nearer and nearer to each other. However, it's not the same value as the value of the function. All right, so the limit as x approaches -3 of g of x does not equal f of, oops, that should be -1, sorry, does not equal f of -1. And then finally, in a situation like where x is 1, there is no point at all when x is equal to 1. So g of 1 does not exist. That should be g as well. All right. State 2 intervals in which g is continuous. Well, there's an infinite number of intervals, but why don't we just pick, say, this interval right here and that interval right there. All right. So we're looking at -3 to -1. Now we know that we have discontinuities at x equals -3 and x equals -1, so we don't want to have a closed interval. We want an open interval, so we're going to use parentheses. Remember, you could also write this as -3 is less than x is less than -1. Oops, let me get that on the page there for you. Sorry. Either one of those would be fine. This region right here is the interval from 1 to 4. So that notation works, or we could also have 1 is less than x is less than 4. All right, with number 2, f is this piecewise defined function. We have to show that f is continuous at x equals 2. First thing, show that the function exists at x equals 2. Well, right there we see that when x is 2, the function is equal to 2x squared minus 3. So f of 2 equals 2 times 2 squared minus 3. 2 squared is 4, doubled is 8, minus 3 is 5. All right, done. Step 2, we need to show that the limit as x approaches 2 of the function exists. All right, in order for this to be true, we have to look both at the limit as x approaches 2 from the left of the function and also the limit as x approaches 2 from the right of the function. All right, when x approaches 2 from the left, those are numbers that are smaller than 2. That means we're using this condition, so we're going to use the top function again. Now we're looking at 1.999, but that's so close to 2 we can just use 2, and we've actually already plugged 2 into that function. We get 5. If we look at the limit as x approaches 2 from the right, well, now we're talking about numbers that are larger than 2. So we're in the bottom condition, which means we need to use 3x minus 1. So this is equal to 3 times 2 minus 1, which also happens to be 5. The left limit is 5, the right limit is 5, so the limit in general is 5. Condition number 2 has been met. Now we need to talk about condition number 3. The value of the function must be equal to the value of the limit. Well, the cool thing about 5 is that it's equal to itself. So we're all set here. Finally, with number 3, we have to circle the following functions which are continuous over the domain of all real numbers. All right, so what do we have here? Well, cosine, that's continuous over the domain of all real numbers, as is e to the x. Those two functions can be drawn without picking our pen up off the paper. In addition to that, e to the -2x, doesn't matter what the exponent is. Well, actually, technically it does matter, but whether the exponent is -2x or x, e is still going to be continuous. So that's another one that we can circle. Sine of 3 over x is definitely out because if x is 0, that function's in trouble. This one's definitely out because if x is 1, that function is in trouble. Natural log of x, we cannot have any inputs which are negative for x. We want the domain of all real numbers. That's out, as is the square root of x, because the square root of x, if x is negative, we're no longer in the real number system. Well, over here we have x to the negative 2, which we know can be rewritten as 1 over x squared. Once again, like over here, if x is 0, that's bad. Cosecant of x, one of the graphs that we're looking to memorize, that's one that has a lot of parabolas, but I can't draw all those parabolas without taking my pen off the paper. Cosecant is out. And x equals, x to the 1/3, that's the same thing as the cube root of x. The cube root of x and the fifth root of x behave the same way. They are both functions which behave something like that, but they can be drawn from negative infinity to positive infinity without picking our pen up off the paper. They are continuous for all real numbers, as is the absolute value of x, which is our basic V graph.